that called for a 20% energy savings target across their entire data center portfolio. And for example, Digital Realty and Intel speakers coming up are both partners in the Challenge program. We also have an accelerator partner set that's a 5-year commitment for a 25% reduction in energy, and like LBL is one of those partners. That's a metric, by the way, that's a savings on infrastructure, so it's basically a PUE -1. But we're not only obviously concerned about PUE. The Better Buildings program does encourage partners to look at other performance metrics, and some of them are sort of cutting edge. For example, we're encouraging the use of TUE, which is similar to PUE, but it takes the power from the fans and the power supplies in the IT equipment and puts that into the facility side. It's especially important in the high-performance computing or supercomputer arena where the power supply and fans sometimes are inside the box and sometimes outside of the box. So for a real fair comparison, you need to look at that total. We're also encouraging the use of WUE, which is a metric for water efficiency, although we have to be careful that we don't save water at the site and use more water at the power plant where the energy that is required to, say, run a air-cooled chiller is more than what's required to run a liquid-cooled chiller. We're looking at energy recovery and how much of the heat from the data center is reused, some productively somewhere else. That's a metric. And then renewable energy contribution is a metric. And of course, the holy grail, and we'll hear at least one speaker address this today, is the computational performance. And how is the computational performance compared to the energy in? And that's, again, a very difficult metric, but sometimes we do or have the capability to do it, at least for ourselves. Very difficult to do it across data centers. So with that, we'll go to the first speaker, Aaron.
Thanks, Dale. So I'm going to take maybe a different approach around metrics and energy efficiency. Digital Realty is in 12 countries with about 200 data centers, serving from interconnection all the way up through hyperscale. As a sustainability guy, I feel obligated to talk about sustainability for just a minute. We do have a successful track record of sustainability focused on energy efficiency, which we'll talk about in more detail, green buildings, as well as renewable energy sourcing, and a few other fun initiatives along the way. So I'll posit to you a metric of the future should be BUE, budget utilization effectiveness. So how are the dollars that you're investing to make your building more energy efficient getting to the point where they're actually delivering the greatest value for your data center? So we think about this in terms of our Eco Project program. So this is really identifying energy conservation opportunities, or eco opportunities, within our portfolio of data centers. We understand who the beneficiaries of those actual energy savings are. Is it Digital Realty, the landlord? Is it a customer? Is it shared? And how is it shared? And then how do we allocate capital to those projects appropriately, given a diverse and extensive range of capital obligations that we have at these facilities at any given time? So I won't go through the metrics, but let's just say we do this program, we boil the ocean, we identify lots of projects, lots of opportunities, lots of places where we can invest capital, and lots of places where we can save energy and resources. So we think about this in terms of buckets to be very simple. There's an eco bucket and there's a traditional CapEx bucket. In the eco bucket, it's anything that, to oversimplify, it's anything that has an energy efficiency element to it. So this could be a pure energy savings opportunity. It could also be end-of-life equipment upgrades, that the new equipment is just more energy efficient because the technology has advanced, and anything in between. On the traditional side, maybe the cleanest example is repaving the parking lot. Obviously no energy efficiency savings to that, but something that has to be done periodically. So we split the stack as we look at capital investment opportunities in the properties. When we look at that, we then say, where do these benefits go? So this kind of ties back to the BUE concept. So are we utilizing an investment in that property in an effective way to get the greatest benefit for the stakeholders that we're trying to serve? And in some cases, it's digital realty. In some cases, it may be a particular customer or set of customers. And in some cases, both. So we look at this, in this case, highlighting our colo footprint, energy savings targets that we've achieved, energy savings targets that we're moving toward and continuing to achieve in 18 and likely in 19 and beyond. So when we look at these are projects that are very specifically tied to energy savings, and there are many other projects that have been implemented. But what do you notice about the budget, the incentives, the annualized savings? These are projects that pay for themselves in a year. These are compelling investments. So if these were competing for the same capital that the parking lot repaving was competing for, you'd have to really understand the value proposition of this and why it's much more compelling in some ways than another project that might make the facility look a lot nicer. In this case, these projects actually directly benefit digital realty. We have a slate of projects that also benefit our customers in the buildings as well. So when we think about this BUE concept, we also look at it on new construction and transitioning those new developments into the operations phase. So in our Chicago land area, we have several large data center campuses there. And as we've built those out, we've worked very closely with the local utility to make sure that we're optimizing energy efficiency, both in the design of the data centers, as well as in their ongoing operations, once we start bringing customers in, once we start ramping up their loads. So what we've done is we've said, let's set an aggressive baseline for PUE. Let's exceed that baseline through improvements and design tweaks to get to a really top flight multi-tenant data center environment. What this gets to, and this is how it ties back to this BUE concept, is not only are you leveraging the innate efficiency and value of an investment in energy conservation. So you're saying, I'm investing $1, I'm getting some amount of lower energy operating costs out of it. But what we're also doing here, and the reason I highlight this, is that by working closely with the utility, we're able to further bring down the cost of those projects, those improvements, and those investments to make the case even stronger that the budget utilization and effectiveness for these improvements to bring that PUE down are good investments. The utility sees that, they save energy, they improve their ability to serve their customers reliably, and they pass that benefit on through incentive programs that support energy efficient data center operations. And I can't take any credit for this. There's a whole team of folks that work diligently over multiple years between design, construction, and operations to get this done. A few of them are highlighted here, and I think a couple of them might even be in the room. So with that, I'll close, and I'll propose the BUE metric for you for consideration.
Hi everybody. I'm Nissim, data center engineer in Intel Santa Clara. I work about 20 years in Intel. Started as an electrical engineer, and now I'm a data center engineer. I would like to share with you some information about high density data centers in Intel and are very efficient data centers with a very low PUE. We'll show you how we were able to make it. All the information that I'm going to present is posted in IT@intel.com in white papers. There were some articles in the Wall Street journals and some other technical websites. They were all impressed from our data centers, so you can go to IT@intel.com and get more information. So you all know when you start designing a data center, you have to consider a lot of things, industry standards, local standards, international, the tier level that you want to do, the data center cost and reliability. Growth in compute demand, you know, we also in the first presentation that there is a 30% year-over-year growth in computing. It's amazing, and we need to take this into account when we build data center and make sure we have a future availability to increase capacity. At the bottom you can see some details about the climate in California, because those data centers were built in California, and it was important to find out how the climate looked like in California, especially in the Bay Area. There are other things that I don't show here, ASHRAE guidelines and standards. We also consider the ASHRAE, so, and there are more, seismic zone and stuff like that. So I like to present the first data center, the free air cooling. So about 5 years ago, we decided to build a 5 megawatt of data center, and we decided to make it with only free air cooling. We were able to achieve with this data center a PUE that is 0.6. We designed for 1.07, but we'll see now that we are at 0.6. The idea in this data center, we just take air from outside, filter it, bring it to the cold aisle. The hot air that goes through the server, that produce after the servers, leave the building. In the cold days, what we do, we take the hot air, we mix it with the cold air, with the incoming air, because we don't want to bring too cold air temperature in the cold days during the night especially. So sometimes we mix the air, but most of the time the hot air leaves the building and we don't do nothing with it. So it's a simple concept. Basically what you need is air handler units on the top and just fans that push the airs. The two buses that you see, just to give you an idea how big the ducts that transfer the air. A lot of volume of air goes into this 5 megawatt data center. We ran some airflow model to show that the concept work and we don't have issue with temperature. Sometime during the hot days when the temperature goes above 90 Fahrenheit, we're using chillers. So there are only few days during the year in the Bay Area. This does not impact the PUE. The average is still low if you look at the annual PUE. So even when the chiller kicks in, we're still below the 1.7, 1.6. The temperature in the hot aisle, the cold aisle, can go up to 95 without any issues. If you take a server specification and look at, range, temperature range, humidity, the vendor tells you you can operate it up to 90 Fahrenheit. So why reduce the temperature to 78? Traditional 78, 80 Fahrenheit. So sometimes the temperature goes up to 90. The chiller doesn't kick in, and no issue with this data center. It's already runs 5 years. We didn't see any performance issue with the servers. Everything works still the same. One major design that we did also in the racks, you all know that a standard rack cabinet is 24 inches. 20 inches plus 2 and 2 inches on the side for cable management. In this data center and the other one, what we did is eliminated the 4 inches and we just have the 20 inches. So for every 5 cabinets, we gain space for another cabinet. So this is why we consider it a very high density data center, plus the 60U. All of our racks in this data center and the next one are 60U cabinets. And each cabinet is 43 kilowatt per rack. The other data center, which is much bigger than the first one, is a 31 megawatt of data center of servers. We just built it 3 years ago. Right now, half of it already populated with servers. So we have a good idea how the concept works. The main idea here is that, in a traditional cooling system, you have cooling towers, chillers, crack units inside the data center, res metal floor. So we eliminated the chillers. This is the largest consumption equipment in this loop. So we don't have a chiller in this concept. We only have a cooling tower and a first loop for the cooling tower, heat exchanger, and then a secondary loop. The water goes in the secondary loop to the coils above the Hanheim. Those coils are